This is a quick run-through of 5 pages on Proteopedia. It's one way of preserving the content by just taking a movie. We made this in 2022 in a Biochemistry 2 class. It's about carbon metabolism. I won't go through the details. This is a page that just has text and animated GIFs. So not a typical Proteopedia page, but I'm starting here because it links to the 4 pages I want to show. There's a revision history that shows that this was made in 2022. I created this, the instructor, as a glue for the 4 pages that the students made or revised. One of them was pre-existing. So this starts out with methylene tetrahydrofolate, and I'm showing 2 paths. The first one is to put a methyl on UMP, so it becomes TMP, or DUMP. So there's some static images there, and soon we'll see the superpower of Proteopedia, which is a browser for JMOL. I'm not going to talk the whole time, so just when there's something that I want to point out. So here we begin to see the browser, and there's a second slider so that you can go ahead and see the text while you're watching or interacting with the browser. The green links bring up the next scene. So I believe this is to show the active site with the substrate bound, and you can see the interactions on the left, static, and then on the right you can explore them. You can rotate the orientation, and you can hover over things to see what they are, and you can also click and measure distances, which I'll do in a second here. This is not a relevant distance, but that's just to demonstrate the capabilities. So this is a way of showing the intermediate in the reaction pathway, and in order to do that, they switched a carbonyl group to an amine group, and I'm trying to find that part. But if you wait a second, there's actually in the text there's also a little highlighter that I'm going to click on in a second once I realize that's there. Anyway, you can zoom in, you can zoom out, you can change the orientation, you can identify different elements of the structure that you're looking at by hovering and, as I said, measuring things by clicking. So here's the highlighter. So that's the atom that was modified, or the functional group, making sure that it stops at this stage and doesn't go to the next. I didn't mention there are captions for all the images, so when you click on the green link, the caption changes too, and often it tells you the currently 4-digit identifier for the PDB file for the protein database. This is the first time you see these buttons, so there's 2 structures or 2 conformations. And we can go back and forth with them or show them both at the same time. Last section is about inhibitors. This is in real time, so you can get a sense of how long it takes to load. So this shows the environment of the inhibitor. the articles have references, and it says who are the contributors and editors. So back to our overview, and now we're looking at a different pathway where we're actually putting a methyl on methionine. So first, the folate gets reduced. So this is a redox enzyme that uses NADPH as the redox partner. And as it gets reduced, it's also opening up one bond. So we get the methylated folate, tetrahydrofolate. This enzyme has a classic mechanism called ping pong. You do one reaction, then you swap out one of the substrates, and then you do the second reaction. And what mediates this is the FADH2, and FADH that's bound permanently to the enzyme. And so this shows it in 3D now. There's two structures, one with the NADH bound and the other one with the tetrahydrofolate. Okay, so once the methyl group has been transferred, there's one more step, which is activating the methionine to turn it into S-adenosyl methionine. Oh, sorry, messed up. It's the transfer from the methyl tetrahydrofolate to homocysteine to turn it into methionine. So that's the methyl transfer. It's cobalt mediated. There's a cobalt in the enzyme. The enzyme sometimes gets the wrong oxidation state and then has to be regenerated. So the quick step that's shown here is the usual, and then the longer step is a series of steps, the regeneration. So one sign of the times is that there was no structure of the complete enzyme. Fragments had been solved, functional fragments. So we used AlphaFold to get a predicted entire structure. But it turns out that there are structures of domain 1 and 2, and then structures of domain 3 and 4. So most of the structures known, and you can see here the confidence of AlphaFold shows that clearly, that there's a block that's known and another block that's known, and the orientation between them is unknown. On the left, there's a 2D image of the cofactor, the vitamin, cobalamin, that binds to the cobalt. So it's vitamin B12. So it binds. There's the cobalt. B12 has been called a supernucleotide, nucleophile, sorry. So it's super reactive, and there's a cap domain that sort of protects it from reacting when it's not in action. And again, there's these interactive elements that you can show it in one or the other conformation, or even in both, which is confusing. So this is with the cap, and this is without the cap. And the last bit is about this reactivation. If the cobalt is in the wrong oxidation state, then the enzyme expends some extra free energy to get it back into the right oxidation state and put the methyl back on it, so that it can cycle through the actual reaction that it wants to do, which is methylating the homocysteine to make methionine. Okay, so now that we have methionine, we do have to activate it into S-adenosyl methionine. So that's the reaction with ATP, where we're not using the triphosphate to drive something, but also we're covalently attaching the ATP to the methionine, which becomes SAM, the sort of general methylation cofactor used in DNA methylation. And so you already know the drill now. This is the first the reaction scheme, and then we get scrolling down, we get to the part where we can see some structural data in the browser and interact with it. So this is a quaternary structure. It's tetramers. And it turns out that the active site is in between two of the subunits. So this is one thing that JML can do, these smooth transitions from one scene to the next, which maintains sort of the awareness, which orientation the molecule's at while you're changing details. So this is a different enzyme, and I believe this is an image that this is one of the articles we revised, and this is one of the original images. From the same enzyme, but different organism. So now we're taking a close look at the substrates. So on the bottom with the yellow, that's the methionine, and on top is the ATP. And there's a regulatory subunit, I believe the green one, that modulates activity. And this is also about regulation, so there's a gating loop. Above the active site. And so depending on its conformation, you get activity or not.